Welcome to your favourite podcast.
Hello and welcome back to the Copper Connection podcast, the podcast where we dive deep into the essential principles of construction and building services. As always, I'm your host, Chris Bentley, and today we're tackling episode 15, where we explore the fascinating world of structural science principles, a critical component of construction science principles. Whether you're a seasoned professional, a student, or someone just curious about how buildings stand tall and withstand the forces of nature, this episode is for you. We'll be breaking down everything from forces acting on buildings to the calculations that keep structures safe and sound. So grab your coffee, settle in, and let's connect with the science that holds our world together. Let's start with the basics. When we're looking at a building, whether it's a towering skyscraper or a modest home, we are looking at structure that consistently battles forces. Gravity is pulling it down, wind is pushing against it, and if you're in certain parts of the world, earthquakes are shaking it. Added to the everyday occupation, people walking around, furniture being moved, equipment running, and you've got a complex web of forces acting on the building's primary superstructure. This is where structural science comes in. During the design phase, engineers must calculate whether the building and the materials used can withstand all the forces. It's not just about making something that looks good, it's about making something that won't collapse. Now, when we talk about forces on a building, we need to understand two key concepts. They are dead loads and live loads. Dead loads are static, they don't move. Think of weight of the walls themselves, the ceilings, the floors. These are permanent fixtures that are always exerting force on the structure. Then we have live loads, on the other hand, are variable. They come from the occupation of the building. So furniture, equipment, people moving around, these are all live loads that change over time. The structural frame of a building, primarily made up of beams and columns, is designed to handle both types of loads. Beams transfer the total load to the columns, and the columns carry the load down to the foundations, providing stability to the entire structure. It's a beautiful system when you think about it. Everything works together and keeps the building upright. Now, let's talk about the different types of forces that act on structural materials. There are four main ones you need to know. First, compression. This is the force that essentially crushes a material. Imagine stacking heavy books on top of a cardboard box. That's compression in action. Columns in the building experience massive compression forces as they support the weight of everything above them. Second, we have tension. This is the opposite. It's tearing apart force. Think of a rope in tug of war. In buildings, tension acts on elements like ties and struts in the roof structure. Third, we have bending. This is about the amount of force and distance from a reaction point, which we call the bending moment. When you stand in the middle of a plank of wood suspended by two supports, you are creating a bending force. And fourth, we have shear. This is a bit tricky to visualize. Imagine a bolt holding two structural members together. If there's an axial force trying to slide these members past each other, that bolt could be sheared in half. It's like trying to cut through something with scissors. That's a shearing action. There's also torsion, which is a twisting force applied by rotation. Think of wringing out a wet towel. That twisting motion is torsion. Beyond the types of forces, we also need to consider the direction of loads. There are three main types. We have vertical loads, or straight down forces acting under gravity. This is the most common type we think about, the weight of everything pressing down. Then we have horizontal loads, come from forces like wind pressing on the side of a building. If you have ever been in a tall building on a windy day and you felt it sway slightly, that's the structure responding to horizontal loads. Then we have longitudinal loads, act along a length. Great example is the tension in a railway line due to heat expansion in the summer. The metal expands, creating forces along its length. Now let's shift gears and talk about the load-bearing structures. A load-bearing wall is an active structural element. It supports vertical loads and transfer loads from the roof, walls and floors down to the foundations. This type of construction dates back to the earliest forms of buildings. However, in modern high-rise construction, we use something called skeleton frame construction instead. This allows for multiple floors and much greater building heights than traditional load-bearing walls could support. It's one of the innovations that's made our modern skylines possible. When we're selecting materials for load-bearing structures, we need to consider several properties. First, we have strength, the ability to withstand force. Not all materials are created equal here. Then we have malleability, the ability to change in shape without failing or buckling. Then we have hardness, the ability to resist impact and remain undeformed. And then elasticity, the ability to stretch and then return to its original shape. Here's an interesting historical note. Raw iron has been heated and worked into shape, has much higher tensile strength than cast iron, which is molten metal poured into a mould. Because raw iron resists fatigue so well, it was used for horizontal beams in construction, particularly in bridges. Today, steel has largely replaced raw iron, but the principle still remains the same. Now let's talk about the structural members that make up a building. At the bottom, we have the footings or foundations. These are crucial for distributing the building's load into the ground safely. Moving up, we have the walls, then the beams and the columns. From the skeleton of the structure, and finally roof trusses, which supports the roof and transfers its load down through the rest of the structure. Each of these members experiences stresses and strains. Stress is the internal force per unit area within a material, while strain is the deformation or change in a shape that results from that stress. Understanding the relationship between stress and strain is fundamental to structural design. Here's something that's particularly relevant for those of you in the trades. When you're installing pipework or cabling, you might need to notch or drill through floors or ceiling joists. But here's the critical thing. This could weaken those joists to the point where they become structurally unsound. You absolutely must understand and calculate permitted notching zones and maximum depths of holes and notches. The locations and depth depend on the span of the timber joist and its depth. So, for example, a timber with a depth of 200 millimeters can have a hole no larger than 50 millimeters in diameter and 25 millimeters in depth. These calculations are subject to quite complex guidance, and getting them wrong could compromise the entire structure. There's excellent guides available, including the one from LABC that shows safe hole and notching locations and relative hole sizes. All of these calculations we've been discussing aren't just best practice. They are required by building control to comply with approved document A, which is structure, which is part of the building regulations. This calculation must provide that sufficient safety factors have been engineered into a structure so it's safe for occupation. Part A covers structural work in steel, concrete, timber, masonry and aluminium. It specifies dimensions and thicknesses required and includes requirements for foundations, wall cladding and roof coverings. If you are working in construction, you should thoroughly familiarise yourself with this document. Finally, let's talk about external factors. Ground conditions are hugely important for determining how surface loads are transmitted into the ground safely for the lifespan of the structure. You need to consider things like settlement, how compressible is the ground, and climate conditions. Buildings over a drain or sewer is another consideration. This could cause damage or make access difficult for maintenance or repair, so there are regulations governing what's permitted. And here's something many people don't think about: trees. The growth of nearby trees and their roots can cause serious damage to foundations. This can be avoided by locating structures and services at a safe distance. The NHBC standards provide excellent guidance on building near trees and the precautions required. All of these factors, adjacent structures, trees, drains, sewers, and ground conditions, must be carefully considered in the design of foundations. Okay, and that wraps up episode 15 of the Copper Connection podcast, where we've covered a lot of ground today, from the fundamental forces acting on a building to the critical calculations that keep structures safe and compliant with building regulations. The key takeaway: structural science isn't just about numbers and formulas. It's about understanding how forces work, how materials respond, and how all the elements of a building work together as a system. Whether you're designing a structure, installing services, or just maintaining a building, this knowledge is fundamental. If you have found this episode helpful, please subscribe and share it with your colleagues. And if you have a question or topic that you'd like us to cover in future episodes, please reach out to us on our social media. Until next time, stay safe, stay curious, and keep those connections moving.
We'll be back next week. In the meantime, please subscribe and thanks for listening.